Hello everyone, welcome back to Automotive Code 2025. It's time for the last day of the year, now that we have the abbreviated 12-day schedule. I still think I appreciate this. 25 days is a lot. And it was, it's been a long time since I made it through the whole year. I appreciate having a somewhat more approachable number of puzzles. 8, 9, and 10, I think, were the ones that took me way longer than I would have liked. All the others were reasonably short-ish. It would be nice to go back and finish day 10. I'm not going to do that on video. I might do it on my own time someday. We'll see. Day 12, Christmas Tree Farm. You're almost out of time, but there can't be that much left to decorate. Well, there can't be much left to decorate. Although there are no stairs, elevators, escalators, tunnels, chutes, teleporters, fire poles, or conduits here that would take you deeper into the North Pole base, there is a ventilation duct. You jump in. After bumping around for a few minutes, you emerge from a large, well-lit cavern full of Christmas trees. There are a few elves here frantically decorating before the deadline. They think they'll be able to finish most of the work, but the one thing they're worried about is the presents for all the young elves that live here at the North Pole. It's an ancient tradition to put the presents under the trees, but the elves are worried they won't fit. The presents come in a few standard but very weird shapes. The shapes and the regions into which they need to fit are all measured in standard units. To be aesthetically pleasing, the presents need to be placed into the regions in a way that follows a standardized two-dimensional unit grid. You also can't stack presents. As always, the elves have a summary of the situation. First, it contains a list of the presents' shapes. Second, it contains the size of the region under each tree and a list of the number of presents of each shape that need to fit into that region. Oh my god. I don't know a good algorithm for this. Yeah, so here's all the kinds of shapes that the presents have. 5 is probably a bike. For convenience, yeah. Second section lists the regions under the tree. It line starts with the width and length of the region. Yeah, so they're rectangles. Describe the presents that need to fit using the quantity of each shape. Yeah, one present with the shape index 2. Yeah. Okay. Presents can be rotated and flipped. Yep. They can't overlap, but they can fit together. A dot and a hash. Yep. Yikes. Yeah, the first region is 4x4 and just needs 2 copies of shape number 4. This one. And so indeed, here's how you could fit them. Oh boy. I have no idea what an efficient not polygon, like polyomino layout algorithm looks like. Isn't this like a bin packing or backpack type problem, but just made insane by the irregular shapes? Now, some of these regions you could perhaps rule out immediately because the total area of the presence exceeds the total area of the region. But that is going to be... There are going to be many things that don't fit where that's not true. Where, like, yeah, there's enough space, but you just can't twist the presents in the right way, right? So how on earth... could you even start this? I gotta look at my input. Like, how big are these shapes and presents and regions and stuff? They're enormous. Okay. But all of our presents are exactly 3 by 3 in footprint. So, like, in principle, you could, like, find... Instead of starting from a region size and then trying all the ways to place, like... I mean, this is just... That's impossible. That would take forever, right? To place 40... Like, all the places you could place... rotations and reflections of shape 1 46 times. Like, already that, I mean, I don't think you could solve even that with your with the available compute time that you have, probably in a reasonable amount of time. You need something smarter. And I wonder if, like, one idea is to, instead of starting with the regions, start with the shapes. There's only 6 of them. And you could kind of construct compound shapes in a way where, like, for example, shape 1 fits into shape 1 very well by reflecting it and slotting the 2 edges into inlets, right? And that compound shape is kind of the best way to fit 2 1s near each other. But it's not the only way. You might want to stack 2 of them on top of each other, kind of, right? But I don't know. So you could kind of say, well, that's these are the ways we could fit 2 1s together. And then you could say, well, how can we fit a 1 and a 2 together? And now you have a new compound shape that's like a 1-2. Right? But I guess I'm not sure that really helps. Because maybe the way to lay things out in this area is to put all the 1s next to each other, slotted very nicely, and then do something else with all the 2s, and then something with all the 3s. Or maybe it's to have all the 1s hanging out with all the 3s, or half the 1s hanging out with the 3s, and half the 1s hanging out with the 2s, and like, so forming compound shapes is not, I don't think, going to help you very much. Now, I know some words I could Google that would probably lead me to a Wikipedia article on, like, algorithms for solving this kind of problem, right? This is a tetromino tiling problem or something. But, excuse me, polyomino. Omino. I don't know how what ideas I would have for doing this myself. So my ideas of first, like, search the region, just putting down presents at random and backtracking, seems obviously horrible. The second idea of building compound shapes has something to it. But, I mean, I don't see how that could possibly scale well enough. So let's do some Googling adventure. Polyomino tiling? I said stilling or something. Okay, so let's just look up the Wikipedia article for polyomino, I guess. Yeah, planes, these are figures. These are all pentominoes, fine. Okay, table of contents. Enumerations, no, I don't need that. Tiling regions with sets of polyominoes? So that's what I have, right? The input says, like, here are the 6 kinds of polyominoes, and then tile this region with 46 copies of 1, 32 copies of 2, and so on. So this is the right idea. Backtracking? Yeah, okay, so tiling regions of the plane with sets of polyominoes is NP complete. Okay, so pretty hard. And then backtracking. So, well, I guess let's... No, this is just describing backtracking in general, isn't it? Although it's by the same guy who wrote a thing called polyominoes, I guess. But I don't think I can read ACM articles. Maybe I can. Scan quality is atrocious. Boy, this guy just dives right in, huh? Yeah, okay, this is... Okay, I could download the whole PDF, but... I mean, this isn't talking specifically about polyominoes. It's just talking about backtracking in general, which is well known these days. I don't need to read about that. And you often can avoid backtracking when using Haskell, like we did yesterday. Well, no, I don't know. Just use the list monad to enumerate the entire search space, and then find a solution. And the backtracking just sort of happens automatically. So we're not tiling the whole plane. Yeah. So I suppose one thing we could do, which is a heuristic that might help us answer yes on some puzzles, but would not let us answer no, ever, would be to try to find sets of presents that we can combine into perfect rectangles. Because then we know that that set of polyominoes can take up a rectangle of that size. And I mean, geez, that seems like it would simplify the problem, but I don't know how it would even lead to an answer. Because you'd have to, like, find a set of sets, like a set of ways to split up your actual set of presents into some rectangles such that the number of total presents used equals the number of presents you're supposed to use, right? And even that seems hard. This is crazy. I mean, is there like some... We could, like, compute the smallest rectangle that encloses a set of polyominoes, right? A set of presents. Like, for the set 4 plus 4, that fits into a 4 by 4 rectangle. And leaves 2 open spaces, but let's say we just care that it fits into a 4 by 4. We could then build upon that and say, okay, well, like, say we found the smallest rectangle that every pair of presents could fit into. We could find the smallest rectangle that every trio of presents can fit into. Although I don't think that could even use the result from pairing, because... yeah. Are you kidding me? This problem is impossible. It's NP hard, and the numbers we've been given are large. I mean, they're not like 1 million, but they're not like 2, right? They're 40. And I don't even see how you can... like, generalize is the wrong word, but extend, maybe, from a solution to a smaller problem into a solution for a bigger problem. Let's say I wanted to work on this 12 by 5. I could say, like, you know, okay, well, let's start with a 1 by 1 area, or 3 by 3, I guess, because that's the smallest any present is. I could fit 1 present into that. Then I could look at a 3 by 4 area and say, what can I fit into that? Well, still just 1. But here are the 5 different ways I could do it, maybe. And then I could extend into a 4 by 4 area and say, well, how many things can I fit in here? And I think the answer is all you could fit would be like one of anything or two fours. Actually, I think no, there's probably more. Like two fives should fit as well into a 4x. No, that requires 4x5. So you could do that, but I don't think you could really use the result for how to fit into a 3x4 to help you at all with how to fit into a 4x4. Because you kind of, like, knowing how many ways you can do it in a smaller one doesn't help. You need to know exactly what those ways were so you can see which of those ways can fit another shape in your new larger area. So you just need, like, all the ways you can lay out presents in a 3x3 and in a 3x4 and in a 4x4 and in a 4x5 and in a 5x5. And there's just going to be, like, quadrillions of ways. I'm sure that's an underestimate, probably. So I don't think you can build up from a smaller result to a bigger one efficiently. You kind of just have to do the bigger one. But that seems like... I just can't believe that there's going to be an efficient way to do that. A way to do it. I mean, there must be. This is an additive code problem. Eric doesn't give these out, like, without thinking about them. And then find out they're impossible, or that you would get a Fields Medal or something for completing it. But if you just like, okay, here's an idea for a backtracking approach. Start at the top left point of your region. Arbitrarily choose one of the 6 presents to put there. Great. And make that decision, but be prepared to backtrack if it turns out that's the wrong answer. And this way we'll end up searching the whole graph. What do we do next? What's our next choice? Our next choice is, well, we have to put another present down somewhere. But if we consider both where to put a present and what present to put there, both as part of, like, as separate choices, we're going to really blow up the search space. So I think we should somehow define, given the partially filled grid, there should be only one next place to put a shape. And then you could choose the next shape arbitrarily to put in there and try all its rotations and reflections, which, I mean, I guess means there might be as many as 8 times 6, 48 shapes to put there. And I'm not even sure that that's the right idea. Because, like, you know, if we put down, like, shape 0 rotated counterclockwise once, so these 2 holes are in the top right, that leaves a little slot in the top right that we could maybe fit something usefully in, right? That is, like, part of the space occupied by present 0. But if we put a different shape, there would be a different number of slots available. So even the starting points are not so clear to me. But even if we could uniquely determine a starting point for a shape somehow, and then, like, tile, you know, do this backtracking algorithm, I mean, there would be way too many options, right? How many shapes do we have to put down? Around, you know, 35 times 6? 210? So that would be like 6 to the power of 210 ways to pick what order to put presents down in. Right? That's crazy. You can't ever do that. So that backtracking like just can't be the answer today. And it's not really that big because once we've put down 46 copies of present A, then there's only 5 choices for the later ones, but it's still gigantic. Way too big to just do a backtracking search, even if you could somehow not have to choose a location. So, I mean, I suspect I'm not going to finish today, or I might go look up someone else's answer and then try to understand what they had in mind and re-implement it myself with their ideas. But if I were to find a solution to this, then it can't really be a solution that is generic that could work for all polyominoes. Because if I could do that, I would have a medal, right? They were just saying there is no known good technique. It's NP hard, right? I would be a millionaire if I could write a solution that worked for every set of polyominoes. So if there is a solution today, it probably requires understanding the input better, right? There's something about this set of polyominoes that you can combine them in a relatively small number of ways to form all the useful compound shapes. Like, for example, 5 and 4. These fit together very nicely, right? Into a 4x3, I think. If you just imagine taking 4 and dropping it straight down on 5. Yeah. Then it's a 4x4 with this little dot open. A 3x4 even. And 3 fits into 0 pretty nicely in a couple of ways. Just slotting this little nooks and crannies. A nook is a recess and a cranny is a thing that sticks out, I think. Or are they both recesses? I'm not sure. Anyway, I think this is a cranny here, technically. Fit this cranny into either one of these 2 nooks. And you could have 4 above 0 with the cranny pointing down, or to the right of it reflected with the cranny pointing left, right? It could fit in here. There's a few ways you could fit these into reasonable sized rectangles without much wastage. And then maybe you could tile those rectangles in a way, right? Could you fit a bunch of these together to form a perfect rectangle that happens to be, these are about 7 times 6, about 42. Could you happen to fit these together into a rectangle that's about 7 by 6? One of each of them. That would simplify my life a lot, right? Maybe you could. But that still wouldn't let me answer no confidently. Because there might be another way of tiling them that's a bit better that doesn't use these rectangles. So I don't know. I mean, I think I give up on this. I can't even imagine an algorithm. I mean, I've imagined some algorithms, but I can't imagine one that would be sufficient to answer all these questions. Like, could I even solve the test input, I guess, is a question. I don't know. I'm not so sure. So here they... I mean, like... This is sort of suggestive, right? It points out, look, you can tile two ace shapes with each other in a 5x3 region. That leaves a little bit of a gap here and here. Or 5x4, I guess. Which I saw earlier. And look, you can tile, like, this shape with the cranny into the shape with two missing corners reasonably well. You can tile this U shape into itself. So it's sort of like Eric's trying to hint to us to think about efficient ways to combine a small number. Like, this solution is mostly just a compound of three subsolutions. We take two U's and jam them together and declare that's the entire left third of the grid. Then we take a cranny thing and a missing corner thing and put them together and say that's the middle of the grid. And we put two H's together and say that's the right of the grid. Now, how do I fit those three subgrids together? But I just don't see how that scales. Like, a general algorithm for any set of polynomials is polyominoes is NP hard. So we can't have one of those. We can't possibly come up with one. Well, for an arbitrary, I mean, it depends on the size of the region, and right, like, if they defined 100 different polyominoes, each of which fits into a 3x3 grid, and then said you got to fit 5 presents into this 600 by 600 grid, I would say yeah, I don't have to do any tiling. I just know the answer to that is yes. Right? And equally, if they said you got to fit 36 presents into this 5x5 grid, I would say no, I'm pretty sure I can't do that. So somewhere in the middle there, where it sort of is, where it gets to be close to being doable, but just barely doable or just barely not doable, is where it's NP hard. But maybe we're given enough slack or little enough slack that we can solve it. Like, I guess one thing we could start with that would be sort of interesting to get kind of a pulse on the problem at least, is to compute how much slack we have to work with. Right? Like, imagine we could pack all the presents perfectly with no wasted space at all. And we could fit it into whatever shape rectangle we wanted. how much area do all the presidents take up? And how much area are we being asked to fill in? If one is bigger than the other, like if we have less area than total footprint of all the presidents individually, we can say the problem is impossible. And if we have a ton of slack, the problem is just easy. But if we have a modest amount of slack, the problem is hard. So I guess that's worth at least, even though I don't think I'll be able to finish the problem today, that's at least something we could determine. So let me actually just go borrow my imports from yesterday, I guess, for textrec explicative. And I also need this. I guess I need maps too, huh? So let's define a well, okay, I said yesterday that I love defining generic types like this. Let's do that today. So a 3 is a triple of something. And a present is just 3 3s of something, right? Well, present kind of, I guess, is this. So a present is basically 9 booleans. And I remember there was some cute like you can derive a bunch of instances for this, like, well, so 3 should be foldable, traversable, and a functor, no problem. Oh, right. I have to... A present is 3 bools. I have to use the data constructor for present. Yeah. So now we can do things like, sum of 3, 1, 2, 6, and that's 9. Because of foldable. And we could say fmap successor over this, and we get 2, 3, 7. So all these type classes it participates in. The annoying thing is applicative, which you can implement yourself, but there's some way to derive it via generically. Let me go... Yeah. So here's an example. Where I derive Generic 1 and then applicative via generically 1, huh? And we probably have to add deriving via. We also have to import like GHC generics or something? Yeah. Right, let's put this in here for fun. Oops. And then I can say generic 1. Is that what we were supposed to derive? Yeah. And then we can say, oops. I think it is better to have 3 of 3 of A be generic so that we can have it. Well, no. I think having this be concrete probably makes sense. Of course, it's not coord, it's 3, please. Yeah. And so now we can say, like, 3 is itself applicative. What does that mean exactly? I always... I guess what it means is I can do something like this. Lift A to plus of, well, I guess usually plus mapped over 3, 1, 2, 3, 3, 4, 5, 6. Yeah. So it exposes a way to deal with 3's pointwise. Is what applicative gives you. And by deriving that via generically, we get that without having to actually write it ourselves. Okay. And that, I think, is what lets us write a parser for 3's. Is that true? It's like you traverse... Yeah, because then if I had a 3 of parsers, I could sequence A it into a parser of 3's. That's the point. And you need applicative for that, I think. Maybe you just need traversable, I don't remember. So, I mean, I don't know. Let's... Oh, our input is, I mean, it's a lot of things, isn't it? It's an input containing, first, a list of present. With the indices being implied, we'll just ignore those basically. And then a list of region basically, where I mean, I don't even... region is just 2 ints, I think. No. We don't have a list of regions. We have a list of problems. A problem contains a region and then a list of ints. So this, we can at least write the parser today. We can say we got one thing done before giving up. And then we can even count out which problems are obviously, like how hard is each problem. We can figure that out too. And then give up. Where input is problem, nope, input of do I have some or many in scope? Which one do I have? I have many, that's fine. Many present. And then I guess just many problem. I think that's basically it. Of course, I have to define present and problem, but I think that's all you have to do for input. A present is, I do have decimal, okay. Let's say it's a label, because we're going to just throw away the whole label, basically. A label followed by so here I'm trying to be cute and figure out how to use the applicative and foldable instances to do the parsing automatically. Because, like, what I want to do is 3 times parse something, like the same thing. So I think sequence A of pure, and this pure is going to be in the 3 applicative, and then I'll parse a row, I guess. And it'll infer that I'm in the 3 applicative because I'm passing this as an argument to a list in many present, I think. Each present actually is followed by a new line. A row is sequence A pure no. Sequence A, well, yeah, pure cell, because this will be in 3 again. And then ignore a new line for the end of the row. cell is true after parsing a hash, or false after parsing a dot. And I need or as well. A label is a decimal and then a colon, and then I could import the string function that lets you write multiple characters is one thing, but I mean, I don't have that many strings. It's basically just this one. And let's say that problem is I just want it to be something harmless so I can actually parse the first part and see if it's worked at all. If I write I mean, I guess I can write undefined and see if the rest of it type checks at least. Close. Oh, I never wrapped this up in present, did I? Oh, this was supposed to be capitalized. I thought I caught that I had uncapitalized it, deleted it, and retyped it. It's still lowercase, I guess. Okay, so this parses. That's very exciting. Right, type checks. It compiles. Problem is like really? Oh, yes, that's true. I am saying I parse many problems. Yes, it is difficult to... Okay. That should actually work. As long as I never look at the set of problems. So let's say... Let input shapes nothing equal prepare... I can't show presence. Oh, yeah, I guess not, huh? Show really ought to be all I need. Yeah. And so it parsed all the problems. Isn't that nice? All the presents, I mean. All the handling of threes. I never even had to mention the number 3 anywhere. If I one day decided, you know what? Actually, presence should be a 4 of a 4 of bool. We would just handle it. We would parse 4x4 grids of presence. because we just say pure. We're going to parse each row in the same way, and we're going to parse them one after another. Each row in the same way. And the way we parse a row is to parse 3 cells one after another in the same way. And the way we parse a cell is this. And then just wrap that up in 3s for me. And then turn it around so that instead of a 3 of parser, we have a parser of 3. Kind of cool, right? That was a trick Melissa taught me a couple of years ago, I think. I mean, Melissa is one of the people who's active in the Advent of Code channel on the Functional Programming Discord. I think I linked to her GitHub in a problem last year or 2 years ago because I borrowed something from her. Anyway, not somebody I know personally, just someone on the Discord who is knowledgeable. So we have a parser for presents now. And now if we write a parser for problems, we'll be done with parsing. And the problems are easier than the presents, to be honest. Let's see. So we parsed each row ends with a new line. And each present also ends with a new line. It is a little bit weird and asymmetrical that I'm having rows include their new lines, but presents never mention their new lines, and it's handled up here by input. I'll let it stand, though. So at the time that we're done parsing this last present, we're here, right? We've read the new line at the end of the row as part of the row, and the new line after the present as part of the present, and we're starting right here at the beginning. Okay. So a problem is a problem of a region and many decimals, each being preceded by an ignored space I guess for symmetry, I'll do the same thing up here and have problems end with a new line up there. And a region is a tuple mapped into a decimal followed by an x and then a decimal followed by a colon. I think that's it. Nope. Oh, my parentheses are wrong here. Good. What? Why are you having to default the type? Oh, that's true. I'm throwing away the labels. So you're just inferring what kind of int I wanted to parse. I never told you. That's fine. Can't print problems either. Okay. And then it parses the problems as well. So we have the input now. And I'd be interested in the difficulty of a problem. So let's say we have a function difficulty, or slack, let's say, the amount of slack we have, takes a list of present and a region And then I guess a list of int. This is like a present index. No, it takes a region, of course, you fool. No, it takes a problem. God. And gives me back an int. So, okay. Slack of P's. Problem width, height width doesn't really matter. I usually do things in YX for advent of code, so I guess it should be height width. And then this takes a list of cardinalities. I don't know, equals. Let area, well, let A kind of traditionally equal H times W. Yeah, we don't have, there's no off by one errors there. I guess it can just be area minus footprint, where area is this, and footprint is some zip width times? I think so. Zip width times the map size, I guess, of P's and the cardinalities, and size of present P. I'm unwrapping the present new type, so I just have a 3 of 3 of bool at this point, which means I do have, you know, I have foldable and all this stuff, so I can just say is length filter identity, I guess. Like that. I have to import toList from data foldable. Couldn't match 3 bool with bool. Oh. Of course. Because I don't have a 9 of bool, I have a 3 of 3 of bool. There's some cool operation here that involves traverses, I think. I mean, like, I can call toList and then bind toList, I guess. I don't like it. Yeah, I mean, that works. There's probably something cooler here. but I'll take it for now. So what I want to do is I could have part 1 return a list of int and actually like write a part 1 here, but I guess I'll just do everything in GHCI. Map Slack shapes problems. Interesting. That's a very interesting list here, isn't it? A lot of these are just barely impossible. Well, are very, it's just barely obvious that they're completely impossible, right? Because the area of all the presents exceeds the area we have to work with. And then all the rest, there's a lot of slack. So that's not a proof that any of them are solvable, let alone that all of them are. But it's so much slack, I have to wonder, like, what if I just said all the ones with positive slack are doable and the ones with negative slack aren't? Maybe that's the answer to part 1. I kind of would bet that it's not, but you never know. So they're just asking how many regions can fit all the presents. They don't want to know about the sum of them or anything. So let's try this. Length, filter, greater than or equal to 0, slack, shapes, problems. 557. Really? Were there even that many problems in the list? I guess there were 1,000 of them. I didn't realize it was such a long list. Okay, I mean... Okay, first of all, close the day 11 thing. Where was I? In this window? Okay. Let's just say 557 might be the right answer. Okay, so there is a property of the inputs that makes this solvable, but it's not what I thought it would be about them tiling nicely. It's that we either have not enough space, so little space that it's obviously impossible, or so much space that, well, or a lot of slack, and anytime there's at least one slack, apparently it is solvable. Okay, I'll take it. I don't need map, actually, for part 1 at least. Any other warnings I should address? I'm not using decimal. I probably have to add type applications to the import list. Maybe that's standard these days. It is! Okay. I don't need any sim either, because I only use that temporarily to parse random garbage. Yeah, what do I have? What is my... Okay, yeah, I set my default language to GHC 2021 at some point. GHC 2024 might be ratified or whatever by now, standardized. I don't even know what version of GHC I'm using or who knows what. GHC 2021 has most of the stuff I usually want. So I'll take it. Okay, back to git add p here. Yep. Day 12, part 1. Okay, well, part 2, I imagine, will ask me to do something harder than this. Oh, right. Of course. Part 2 of the final day is always a freebie. It's just, well, if you've done every other problem, you've done this one, and I haven't. Oh. The elves thank you profusely for the help and start rearranging the oddly shaped presents. As you look up, you notice that a lot more elves have arrived here at the Christmas tree farm. In fact, many of these new arrivals look familiar. They're the elves you helped while decorating the North Pole base. What a lovely reunion. Right on schedule, each group seems to have brought a star to put atop one of the Christmas trees. Before any of them can find a ladder, a particularly large Christmas tree suddenly flashes brightly when a large star magically appears above it. As your eyes readjust, you think you notice a portly man with a white beard disappear into the crowd. You go look for a ladder. Only 23 stars to go. Yeah. Well, it sure would be nice to finish day 10, part 2. And have a thrilling conclusion here. Am I going to do that in this video? It's a lot of digging through Hackage docs, or Haddock docs on Hackage, I guess. Ugh. And in the end, it's just like delegating the problem to a smart machine. I guess everything is, though, right? But it's like, I don't know. Skipping out on doing all the algebra myself feels a little bit like cheating, but I don't mind. Learning how to work with Z3 would be a useful endeavor. All right, let's have a look at day 10, part 2. Now that I know all the rest of Advent of Code is out of my way, and I can stop whenever I feel like it. I don't have to worry about like, oh, get this part done so I can do the rest. There's only one thing left. Let me see. Haskell Z3. Oh, that's in bindings for the Z3 theorem prover. Z3 monad. So here we go. Examples. Yeah, give me some examples, please. It now lives somewhere else. That's fine. They renamed the module. Yeah, examples, please. Okay. Is this one anything? Okay, so this just runs all the examples somewhere else. Let's see what... I mean, 4 queens is simple enough. I'm kind of interested in what int list is, but I don't have a list, so I think that's fine. What's the difference between queens 4 all and queens 4? I have no idea. Oh, all the solutions versus 1. Yeah, I don't care about that. So you basically have this monadic interface where you you can make vars, you can define variables. using you can give them names as strings, or you can label them with ints if you prefer. I guess strings is fine. You have to like translate Haskell ints into Z3 ints, whatever, that's fine. And then here they say, okay, there's this assert function, which is an and then T sequences, I think is the one that's from traversable. This is basically a list of assertions. 1 is less than or equal to Q1. 4 is greater than or equal to Q1. So like each queen is in between 1 and 4. And they've put a comment here explaining it. And then they have this distinct that each of them has a different number. We don't really care about that. And they have this diagonal function that checks that queens can't attack each other diagonally. Not or, so none of these are true. And indeed, diagonal is just like join of make eq. That's a little weird, but not my problem, I guess. I don't have to decode why that works. So they in a do context, they create some variables. They make some assertions about those variables based on calling some functions. And then they do this, which says, okay, with model is a function that gets you S3's model, which is its like assignment of values to variables. More complicated than that in ways I don't understand, but for our context, it's just assignments of variables to all the values to all the variables. It gives you that. It calls a function that you want. Inside of the Z3 monad, I guess, so you can never escape. But you can have it be the value of your... So we look at the model, and we ask the model, hey, for each of our queens, what is its value via mapm? Get out of here. I'm not sure what cat maybes is doing. Mapm eval int. This is a list of things. So mapm over it should be a Z3 of list of values. I guess eval int must give you back a maybe for some reason. Okay. And then we cat maybes to throw away any nothing values and return those. And we only look at the second position, which I guess must be the column. Each queen is a tuple, is that right? No. Each one is just an int. Okay. For some reason, eval int returns a tuple of something we don't care about, and then the actual int. And so we're just looking at the actual int. Like this looks doable, right? I could write this. We don't have any arithmetic in here though, right? So I want to know how it handles... Yeah, take me to more examples. Well, hard to know. Maybe mutually recursive handles arithmetic. I mean, I can look in the docs instead of examples, but I'm hoping one of these is pretty simple. No, this is a bunch of Lisp nonsense. Okay, int list. Doesn't look like it. Oh, list AST? Okay, so this is about how they handle lists inside of Z3, which I don't really care about. All right, let's go back and look at the docs for Z3 base. There's a million things here, but let's see how we do arithmetic. Okay, so make add just takes a list. It doesn't just take two things, so that's simple enough. Thank God it's Lisp. Okay. Yeah, I mean, this seems achievable. But I wonder if this is actually the wrong, like maybe it shouldn't be a part of the part 12 video, day 12 video, because I don't really know how long this is going to go. Yeah, I think I'll make this day 13. Day 13 will be finishing day 10. So this is a teaser, I guess, of the kind of AST API we're going to be looking through tomorrow. And there will be a bunch of reading docs, and I think that's a very different kind of thing than you often get with Advent of Code. So if this is interesting to you, understanding how to work with like some other Haskell API, look forward to day 13. And if not, then you don't have to watch the rest of this, I guess. But maybe skip the end of tomorrow's video where hopefully I'll finally have have the reveal of all 24 stars. And if there is no video tomorrow, then guess what? I gave up while I was trying to record it. Either way, I hope you guys have enjoyed the 12 normal days of Christmas with Advent of Code. Thanks for watching, and I'll see you here next year.